Today we're going to talk about a type of proof called indirect proof. When we write indirect proofs, we're going to write them in paragraphs instead of 2 columns. Proofs are taught in geometry classes in high school as 2 columns because that emphasizes to students the importance of justifying everything that you do. That in a proof, you can only say something if you have a good reason for being able to say it, a definition, a postulate, or a theorem. When mathematicians actually write proofs, we don't use 2 columns. We write them out in paragraphs, pages, sometimes books. The longest I've ever done, I think, was maybe like 3 pages typed or something. But I mean, some theorems. There's a man named Andrew Wiles who literally spent 10 years, locked himself in his attic, basically, and worked on this proof. He accomplished it after 10 years of work, and it was actually very anticlimactic for him, because he's like, that was like 10 years, and I did it, and now what? Like, where do I go from here? What do I do now? But so some proofs in math are actually incredibly long. There are many theorems in math that haven't been proven yet, that we believe them to be true. Our experience shows them to be true. We haven't been able to find any examples of them not being true, but we haven't been able to actually prove them true. There's a group of problems called the Millennium Problems, and each of them carries $1 million prize for somebody who would be able to prove these. Most of them deal with prime numbers. Prime numbers are very important in many areas, specifically in internet encryption and keeping the internet secure and safe with like banking websites and credit card websites. And there are a lot of theorems about prime numbers that haven't been able to be proven yet. That if it suits you, you could try that and maybe win $1 million. Today we're going to be writing our proofs in paragraphs. They will not be books or pages long. Maybe at most 7-ish sentences long. An indirect proof is one specific kind of a proof. In an indirect proof, what we're going to do is have 4 main steps. Every time we have the same structure of the same 4 main steps. We are going to begin by assuming the opposite of what we want to prove. Okay? We're going to assume the opposite of what we want to prove. So an indirect proof only works if what we're trying to prove has a clear-cut opposite. There can't be any gray area. It has to be a black and a white, an equals, not equals kind of a thing. Okay? So in an indirect proof, we're going to start by assuming the opposite of what we want to prove. Our second step is we're going to use the keyword then. And we're going to do some logical reasoning, just like we've done in our regular proofs, and say, then, if this is true, this would be true, this would be true, this would be true, and we're going to do some logical reasoning there. The word because is very important in the then portion of the proof. We still need to justify our answers. So I would say, then, this is true because this definition or postulate or theorem. Okay. After doing some of that reasoning, and that's the portion of these proofs that can grow, right? It could just be 1 sentence, but it could maybe be 3 or 4 sentences in that then part. After doing that, you will reach a contradiction of something we know to be true, typically the given. Okay? So we're going to reach a problem where what we've just said doesn't match up with our given. So we're going to say, but we are given that, and state our given, and then we will end the proof by saying, so whatever we want to prove must be true. Okay? Assume, then, but, so is our format. And in that then portion, it's important to use the word because and justify our answers, even though we're not doing it in 2 columns. Our first example is a more numeric or algebraic one, and then we'll do a more geometric one. So our 4 main steps. First thing we're going to do is assume the opposite of what we want to prove. So we're going to assume n is odd. Do not assume the opposite of the given. The given's a fact. Okay? So we're not changing facts. That's the biggest mistake that students make on these, is assuming the opposite of the given. We don't touch the given. We assume the opposite of what we want to prove. Our second portion of our proof is where we say, then, what would be true about it? So if n is odd, and our goal is to reach a contradiction of our given. So our given talks about n squared, so I want to talk about n squared. So then n squared, which is n times n. Okay, well, if n is odd, because that's what we just assumed, and I multiply an odd number by itself, like 1 times 1 is
1.
3 times 3 is 5 times 5 is
25.
Who said 10?
7 times 7 is 49. 9 times 9 is 81. There's nothing special about these particular odd numbers that I'm picking. When you multiply an odd number by an odd number, you get an odd number. So then, n squared, which is n times n, is odd because an odd times an odd is odd. Okay? So we assume the opposite of what we want to prove. Then we do some reasoning, saying because and justifying how we know that. We do that until we've contradicted our given. We just said n squared is odd. Our given says n squared is even. So this is a problem. So then we say, but we are given n squared is even. And we finish our proof by saying, so whatever we want to prove, n is even.
Yeah, really.
Okay? We assume the opposite of what we want to prove, and we find out that that assumption causes a problem. So that means our assumption couldn't have been right, and the opposite of that assumption must actually be what's true. Okay?
Isn't this kind of like, I don't want to say, but isn't it like pointless to, if we know n is even, then we want to assume?
We don't know n is even. That's what we're trying to prove. All we know is n squared is even.
Right. How do you know that? I don't get from saying we're given this, so then
Because we assumed something, and by doing that assumption, we ran into a problem. So our assumption must have been wrong. We use this reasoning in our everyday lives all the time. So some people are quick to make assumptions. I'm kind of one of those people. I'll quickly make an assumption, and often it's not right. And so once I've made that assumption, I'm now going to run into a problem with something. If I make an assumption that somebody understands what I'm saying, and they don't understand what I'm saying, then I'm going to end up running into a problem later. So then I realize my assumption must have been wrong. And that's what we're doing here, is we're making an assumption, showing that it causes a problem, and saying that in the end, so our assumption must have been wrong. And the opposite of that assumption must actually be what's true.
It seems like it works for this, but how is, well, if it's the opposite, how does that prove that the other thing is right?
It can only be if it's a black and white. So n is odd. If it's not odd, it has to be even. Equals has to be not equals. It can't work in gray areas. Yep, so it has to be something where there is a clear-cut opposite. This one's a more geometric example. We are told PQRS is a trapezoid and that PQ and SR are the bases, which means that those are the parallel sides. We learned in our last chapter about trapezoids. We want to prove that PQ does not equal SR. So we are going to begin by saying assume PQ does equal SR. Next we say then, and try to draw some conclusions about what would be true if PQ did equal SR. If PQ did equal SR, then PQ and SR would be both parallel because they're the bases, and congruent. And if PQ and SR are both parallel and congruent, what is true?
It's a parallelogram.
It's a parallelogram. Then PQRS is a parallelogram.
Can we like use symbols to short it?
Yeah, you can use symbols. Because we still need to justify one pair of sides is parallel and congruent. So we learned in our last chapter that one way to prove we have a parallelogram is to show that one set of sides is parallel and congruent. And by assuming those were congruent, that's what we ended up with. This is a problem though, because PQRS is not supposed to be a parallelogram, it's supposed to be a trapezoid. So we say, but we are given that PQRS is a trapezoid. So since we ran into a problem, that means we must have assumed the wrong thing. So PQ does not equal SR. Okay, so we use this logic in our everyday life. We draw assumptions all the time. Some people are more quick to do it than others. But we always draw assumptions, and sometimes we realize along the course of the way that our assumption must have been wrong. And the way we realize that is we run into some sort of a problem. And that's what we're doing here, is we make an assumption, we run into some sort of a problem, and we say, oops, I must have assumed the wrong thing, so the opposite of that must be true, which is what we actually want to prove.
Could this be solved in a two-column proof?
It would be more difficult to solve in a two-column proof. This one definitely lends itself better to indirect. When we're thinking about not equals, things often will lend themselves better to an indirect.
What about equals to?
If it's equals to, then sometimes it could go either way. All right, some examples. I'm just going to read them instead of writing them out. These examples ask you, if we wanted to prove something, what would the first sentence of our indirect proof be? So if I wanted to prove that triangle ABC is equilateral, how would I begin my indirect proof?
Assume it's not equal.
Assume ABC is not equilateral. Okay, we assume the opposite. If I wanted to prove that Doug is Canadian, what would I begin by saying?
Assume Doug is not Canadian.
Assume he is not Canadian. And then I would say something about, then he doesn't like hockey, but he does like hockey, so he must be Canadian or something like that.
He's a Spaniard.
For number 4, if I wanted to prove that A is greater than or equal to B, what would I assume?
That B is greater than A.
A is less than B, which is the same thing as B is greater than A. If I wanted to prove that A is greater than or equal to B, the opposite of greater than or equal to is less than. If I wanted to prove that angle X is greater than angle Y, what is the opposite of that?
Less than or equal to.
Less than or equal to. Make sure when you're changing an inequality that you consider the equal to option as well. And if I wanted to prove that CX isn't a median of triangle ABC, what would I assume?
Yes, it's a median.
Assume it is a median. Assume the opposite of what we want to prove. The first 5 problems are doing just that. Okay? Just writing out what that first sentence would be, assuming the opposite of what you're trying to prove. The first 5 are just writing that first sentence. The other 5 are actually writing indirect proofs.